Pursuing March Madness Perfection, a presentation by me, Jack Binkley, for Stat 512. At the end of every college basketball season, the top 64 teams compete in a bracket-style tournament to determine the national champion, the best team in the country. This time of year is known by many as March Madness. The competition doesn't just stay on the court, though. Outsiders face off with each other to see who has determined the most correct games and who comes out with the best filled-out bracket of the bunch. With a total of 63 games in the tournament and 2 outcomes for each game, the total number of possible bracket combinations is 2 to the 63rd power, or around 9.2 quintillion outcomes. Knowing how difficult it is to randomly choose a perfect bracket, how close could somebody get using statistics from previous years to determine the best outcome of a bracket? In the past few years, new techniques have come to light in the pursuit of this seemingly impossible task. The most well-known form is called bracketology, which is the scientific study of predicting outcomes in a bracketed tourney. Taking statistics used in these studies, as well as involving others that may or may not make an impact, how close can we come to predicting the perfect March Madness bracket? Before we dive in, we must look at how the data is collected. The data used in this project comes from the Pomeroy College Basketball Ratings. These ratings give statistics for each year from 2002 until the most present tournament that occurred in March. The teams at the top of the rankings indicate a good finish to their season and a strong run in the tournament. This data set includes every Division I college basketball team, 357 teams in total. While many years are available, I will use the most recent rankings to see how they compare with the actual results of the tournament. Given the explanatory variables in the dataset, the goal is to determine which predictors have a significant impact on a response variable. More specifically, I wanted to see whether or not factors such as offensive and defensive efficiency in the regular season affect how well a team ranks at the end of the season. Looking at the variables in the original data set, we see that there are 6 variables altogether with a sample size of 357. The response variable will be rank, which is the rank of the team at the end of the season. On top of that, there are 5 explanatory variables, and those are adjusted efficiency margin, adjusted offensive efficiency, adjusted defensive efficiency, the adjusted tempo, and the luck rating, which is the difference between winning percentage and the expected number of wins. I have decided to limit the number of variables used in my exploration when compared to the full set available in the original file. The deleted variables include both categorical and continuous variables that I believe will not assist in determining my desired outcome. The excluded categorical variables include team name, conference, and win-loss record. Excluded continuous variables include the strength of schedule efficiency margins, offensive and defensive rankings, and the non-conference adjusted efficiency margins. Now that the data has been screened, we can begin to look at the preliminary analysis. The first attempt at finding a relationship is through simple linear analysis. A summary plot indicates that the response variable rank has some sort of linear relationship with the adjusted efficiency margin and a decently relevant relationship with adjusted offensive and efficiencies as well. Tempo rating and luck do not seem to have an obvious relationship, but it will be interesting to see their impact with further analysis. We can see similar results when looking at the correlation of each variable in relation to one another. As you can see, adjusted efficiency margin has a strong negative correlation, while the adjusted offensive and defensive efficiencies both show a strong correlation as well. Tempo and luck have very little correlation with rank, with 0.109 and negative 0.002 respectively. Now that we have an understanding of the dataset characteristics, more specifically the relationship of each individual predictor to the response, we can begin to create our model. The first model created is the first order model. This means that each predictor is linearly placed into a model with the response variable. Based on the summary call, we can see that the adjusted R-square value is high, indicating a pretty strong model to begin with. The F statistic generated from the GLT test is significant at a very small p-value. This also means that the predictors do a good job at predicting the response. Next, we must ensure that the model is appropriate for the dataset. This can be done by checking assumptions. The first assumption to check is the constant variance of error terms. This is done by using the Brown-Forsyth test. After running the test, a very small p-value means that this is significant at a level of 0.05. This means there are a sign of non-constant variance, and a better model may be needed down the line. The next assumption to be checked is the normality of error terms. This is done using the Shapiro-Wilks normality test. After running this test, the resulting p-value is again very low and significant at a level of 0.05. This means there are signs of non-normality among the error terms. This is visually evident in the QQ plot as the points deviate from the line in the top right and lower left corners. Failure of this assumption will be needed to be kept in mind when adjusting the model later on. The final assumption to be checked is independence. This can be challenging to check in multiple linear regression, so I decided the best way would be through multi-collinearity. A VIF of larger than 10 signals there could be some sort of multi-collinearity that exists. VIF is only larger than 10 for adjusted efficiency margin, which makes sense. A team with a good offense and defense would in turn have a high margin. This result was expected prior, and therefore it is safe to assume that the assumption for independence has otherwise been met. Now that the assumptions have been checked for the first order model, it is now time to run some diagnostics. The first diagnostics ran involve outliers. By creating a box plot for each predictor variable, outliers become evident as they appear beyond the extremes of the boxes. After seeing where the outliers occur, I double-checked by running Cook's distance and confirmed that outliers are present in every variable. These will be accounted for later on using robust regression to minimize their effect. Before any changes are made to the model, I decided to run automatic model selection and decided to use the best subset method to do this. After seeing the results, it became clear that the model with two predictors was the best subset available for the response. However, the original hypothesis included defensive efficiency, which was not one of the predictors in the subset, so that was added back in. The resulting model contains the response along with adjusted efficiency margin, offensive efficiency, and defensive efficiency. To deal with the problems encountered with the first order model, I decided to run robust regression on the subset with three predictors. After running k-fold cross-validation, the desired result appears to have gotten better. The adjusted R-squared values increased. This means that some of the influence from the outliers has been eliminated. Just like in the first iteration, we have to check the assumptions to make sure improvement has occurred. After running the Brown-Forsyth test again, a p-value higher than the level of 0.05 indicates constant variance of error terms, passing this assumption for the first time. Also, normality of error terms is passed as well, as the points stick to the line much better before trailing off on the extremes. Meeting these assumptions is great news as it means the model is a good way to predict the response variable. This leaves us with our final model. As you can see, there are three predictor variables and one intercept being the response variable rank. Now that the model is finalized, we can go back in and test the hypotheses we had in the beginning. The first hypothesis was, does the adjusted offensive efficiency of a team have a significant impact on its final ranking? The null hypothesis was beta equals 0, where beta is the coefficient for adjusted offensive efficiency. With a t-test statistic of 1.967, it was determined that a p-value of 0.0249 is less than 0.05, and therefore we reject the null hypothesis and consider the coefficient estimate for adjusted offensive efficiency to be statistically significant. Secondly, asking the question, does the adjusted defensive efficiency of a team have a significant impact on its final ranking, we can get a very similar result. We reject the null hypothesis and accept the fact that the coefficient estimate for defensive efficiency is also statistically significant. After finding which variables will assist in determining the final rank of a team, we can now have a better understanding of which teams will do well in the March Madness tournament. This model can be pushed forward and used with future data as long as the predictors are not changed. I came across some issues when gathering my data. The first issue I had was missing information for some of the teams. For example, a total of 3 teams did not have data for their tempo rating. It wasn't that this team scored 0 points a game, it's just that it wasn't entered into the database at the time that I retrieved it. This was countered by using robust regression to limit the number of influential cases rather than eliminating them altogether. When looking back at the beginning, the original model had 5 predictor variables. Of these 5, only 3 were used in the final model. The 2 predictors that were not significant were adjusted tempo rating and luck factor. This concludes my project on the pursuit for the perfect March Madness bracket. Thank you.